All right, hello everyone. For this lecture, we'll be going over section 6.3, which is on the properties of the trigonometric functions. So we have 6 objectives. First, you want to determine the domain and the range of the trigonometric functions. 2, determine the period of the trigonometric functions. 3, determine the signs of the trigonometric functions in a given quadrant. 4, find the values of the trigonometric functions using fundamental identities. 5, find the exact values of the trigonometric functions of an angle given one of the functions in the quadrant of the angle. And 6, use even odd properties to find the exact values of the trigonometric functions. All right, so starting with objective 1, we want to determine the domain and range of trigonometric functions. So from last section, we learned the 6 trigonometric functions. These are sine of theta, cosine of theta, tangent of theta, cosecant of theta, secant of theta, and cotangent of theta. So since sine and theta and cosine of theta won't ever divide by 0, this means that theta can be any angle, which means that the domain of the sine function is all real numbers as well as the domain of the cosine function. So theta can be any value. So domain of sine function is all real numbers as well as cosine function. We can also go ahead and write that both as meaning that they're all real numbers or they exist from negative infinity to positive infinity. Then for tangent and secant functions, they exist everywhere where x is not 0 because we're seeing that we're dividing by x for tangent and secant. So whenever x is not 0, they exist. Therefore, their domains must exclude any values of theta that would have x equals 0. So this means that the domain of the tangent function is the set of all real numbers except for the odd integer multiples of pi over 2, or 90 degrees. This means that the odd integer multiples of pi over 2 have values when x equals 0. This would be pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, those values. Then the domain of the secant function is a set of all real numbers except for odd integer multiples of pi over 2. So the same thing. So for tangent and secant, we're seeing odd integer multiples of pi over 2. Those are the only times when x is equal to 0. Then for cotangent and cosecant, they exist everywhere where y is not 0. So this means that their domains must exclude any values of theta that would have y is equal to 0. So this would mean that the domain of the cotangent and cosecant functions is the set of all real numbers except for the integer multiples of pi. So these are all integer multiples of pi. So this is pi, 2 pi, 3 pi, 4 pi, 5 pi. These are going to be the values where y is equal to 0. So they exist, these functions exist everywhere except for at certain points, then except for sine and cosine. Sine and cosine exist everywhere, while we have secant and tangent exist everywhere except for odd integer multiples of pi over 2, and cotangent, cosecant exist everywhere except for integer multiples of pi. So they have these kind of exceptions for their domains. Now we want to focus on the range. The range of the 6 trigonometric functions for sine and cosine functions, we're thinking about the values that exist for y, now except for x. So for sine and cosine functions, we know that sine theta is equal to y and cosine theta is equal to x, where we know now, and we're thinking of these ranges of values, so the ranges of x and y, x has a range of -1 to 1, and y has a range from -1 to 1 as well. Since we see on the unit circle, the greatest value that they can have is 1 and the lowest they can have is -1. So the ranges then for those functions, so for the ranges for sine of theta and cosine of theta are going to be -1 and 1, saying that -1 is less than or equal to sine or cosine of theta, which is less than or equal to +1. This can also be expressed as writing the absolute value of the functions less than or equal to 1. So absolute value of sine of theta is less than or equal to 1, and the absolute value of cosine of theta is less than or equal to 1. They're the same things, we're just expressing them differently. Then for the cosecant function, If theta is not an integer multiple of pi, or 180 degrees, then we know that cosecant theta is equal to 1 over y. Then we get that since y is equal to sine of theta, and the absolute value of sine of theta is less than or equal to 1, then the absolute value of y is less than or equal to 1. So we get that the absolute value of cosecant of theta is equal to 1 divided by the absolute value of sine of theta, which is equal to 1 divided by the absolute value of y, which is then greater than or equal to 1. So we see 1 over y is going to be less than or equal to -1, or 1 over y is greater than or equal to 1, which then corresponds to cosecant of theta being less than or equal to -1, or cosecant of theta being greater than or equal to 1. So we have our two exceptions there for cosecant. So each one of our trigonometric functions is going to have kind of specifics like this. So then for the secant function, if theta is not an integer multiple of pi over 2 or 90 degrees, then we know that secant theta is equal to 1 over x. Then, similarly to how we got cosecant, we see that that since x is equal to cosine of theta, and the absolute value of x is equal to the absolute value of cosine of x, which is less than or equal to 1, we get that the absolute value of secant of theta is equal to 1 divided by the absolute value of cosine of theta, which is equal to 1 divided by the absolute value of x, which is then greater than or equal to 1. So we're seeing that 1 over x is going to be less than or equal to -1, or 1 over x is going to be greater than or equal to 1. So stating this with our trigonometric functions, now we're saying that secant of theta is less than or equal to -1, or secant of theta is greater than or equal to 1. Then we have that the range of tangent and cotangent functions of the set of all real numbers. So just like before, they exist from -infinity to infinity. So we could write this as -infinity is less than tangent of theta, which is less than infinity. -infinity is less than cotangent of theta, which is less than infinity. So saying all that, here's the table summary for the domain and range of each trigonometric function. So we can look at this table whenever we like. Remember, this table is found in your book, so you can look at this table whenever you'd like to know what your domain and range is of each one of your trigonometric functions. And now you can use this table if you need to in future problems on homeworks and whatnot. All right, so objective 2. We want to determine the period of the trigonometric functions. If we add or subtract integer multiples of 2 pi to theta, the values of sine and cosine would remain unchanged. That is, for all of theta, sine of theta plus 2 pi k, k just meaning that any variation of 2 pi, so k can be like 2, then that would be 2 times 2 pi, so 4 pi. So any multiples of 2 pi really is equal to sine of theta, while cosine of theta plus 2 pi k is equal to cosine of theta, where k is then any integer. So this just means that sine and cosine have a period of 2 pi. That means that the values are going to be the same for every 2 pi that you jump forward or backwards. Then functions that exhibit this behavior are called periodic functions. So sine and cosine are periodic functions. So a function f is called periodic if there is a positive number p with the property that whenever theta is in the domain of f, so is theta plus p. Then f of theta plus p is equal to f of theta. And if there is a smallest such number p, the smallest value is called the fundamental period of f. So that smallest value would be the fundamental period. So the fundamental period of sine and cosine would be 2 pi. So we see that sine and cosine have period of 2 pi. So cosecant and secant also have periods of 2 pi. Since we know that cosecant is just 1 over sine, and secant is 1 over cosine. Tangent and cotangent have periods of pi. So they're the only different ones. Sine, cosine, cosecant, secant all have periods of 2 pi. tangent and cotangent have periods of pi. So for our periodic properties, we see that if we add 2 pi to theta for sine, cosine, cosecant, secant, we end up with the same original values. Then if we have tangent of theta plus pi, that's going to be equal to tangent of theta, and cotangent of theta plus pi is going to be equal to cotangent of theta. So let's go ahead and do an example. So example 1, I want to find the exact value of each of the following angles. So these angles have been simplified already. But for part A, we see we have cosine of 5 pi. Now, it's 5 pi. We don't know exactly what 5 pi is, but we do know that we have a periodic function. So we want to extract as many 2 pi's as we can out of cosine to see what we're then left with, and that would give us our original value. So cosine of 5 pi, well, this can be rewritten as pi plus 2 pi plus 2 pi, which then simplifies to pi plus 4 pi. If you want to think about it, you can also think of this as 2 pi k, or k is now 2. But either way, we simplify to cosine of pi plus 4 pi. We're going to scoop this problem over a little bit so we have some more room. So if this simplifies, this is a multiple of 2 pi. And if it's a multiple of 2 pi, then that means that all it's doing is it's going 2 periods again to give us the same original value as cosine of pi. So this is going to be equal to cosine of pi, where we know that cosine of pi is equal to -1. So then this means cosine of 5 pi is also equal to -1. So all we did was identify the multiple of our period within our parentheses. So now we can do the same thing with tangent. But now with tangent, remember our period is just pi. So we want to extract as many pi's as we can. So now when we have tangent of 5 pi over 4, 5 pi over 4 is the same thing as saying pi plus pi over 4. So we can extract 1 pi out. So this means it went 1 period. So what we see here is that we have 1 period of pi. Come on, there we go, pi. So this means we're going to end up with the same value as we would have with tangent of just pi over 4. Then tangent of pi over 4, remember that would be the square root of 2 over 2 divided by the square root of 2 over 2. So tangent of pi over 4 is going to be 1. So this means that tangent of 5 pi over 4 is going to be 1. So that would be how we would find the exact value of angles that include different periods. So we can always simplify these. Then for objective 3, we want to determine the signs of the trigonometric functions in a given quadrant. So we see that our 6 trigonometric functions can be positive or negative according to what quadrant theta is in. We kind of went over this already when we were working with our multiple integers of specific angles. So here's an illustration and table summarizing when each function is positive or negative. So we're going to zoom in on this a little bit. So in our bigger graph here, we see that in quadrant 1, we have values of x and y that are both positive. In quadrant 2, we see that x is negative and y is positive. So this means that sine of theta is greater than 0, cosecant of theta is greater than 0, and everything else is going to be negative. Because these are the only ones that solely deal with y, which is positive. Then in quadrant 3, we see that x and y are both going to be negative. So tangent of theta is going to be greater than 0, and cotangent of theta is going to be greater than 0, while everything else is negative. Since x and y are negative, if you're just dealing with one, it'll be negative, but when you're dealing with both, it'll be positive. Then quadrant 4, we see that x is positive and y is negative, so cosine of theta is going to be greater than 0, and secant of theta is going to be greater than 0, because these deal with x, and everything else will be negative. Then we see our other values here. So when we're dealing with sine and cosecant, we see that quadrants 1 and 2 are positive, 3 and 4 are negative. When dealing with cosine and secant, we see quadrants 1 and 4 are positive, while 2 and 3 are negative. Then with tangent and cotangent, we see quadrants 1 and 3 are positive, and quadrants 2 and 4 are going to be negative. So then we have a table here as well telling us all the same values. So once again, these are going to be in your book. So if you would like to use these tables as references when working through problems, by all means, use those. Then objective 4, we want to find the values of the trigonometric functions using fundamental identities. So based on our definitions for our trigonometric functions, we can see that we have some reciprocal identities. So reciprocal identities, we're really just looking at cosecant, secant, and cotangent. So cosecant theta is 1 over sine, secant of theta is 1 over cosine, cotangent of theta is 1 over tangent of theta. So these are reciprocal properties. Then we can also state that 2 of our trigonometric functions are quotient properties. These are going to be tangent and cotangent because we're taking a trigonometric function and dividing by another trigonometric function. So tangent of theta is sine of theta divided by cosine of theta, and cotangent of theta is cosine of theta divided by sine of theta. So we're dividing other trigonometric functions. Then, since sine of theta is equal to y and cosine of theta is equal to x, we can use the equation of a circle with the unit circle to get our identity sine squared of theta plus cosine squared of theta is equal to 1. So remember with our equation of a circle, we said that x squared plus y squared is equal to the radius squared. If we combine our trigonometric functions with the idea of the unit circle, that gives us this identity. Since we do use our trigonometric functions with our unit circle, we are allowed to have this identity, which gives us that sine squared theta plus cosine squared theta is equal to 1, or any combination of this. So this could be sine squared of theta is equal to 1 minus cosine squared of theta, or cosine squared of theta is equal to 1 minus sine squared of theta. You can rearrange it as well. Then, to get our next identity, we can divide each side of our last identity, so this identity here, by cosine squared theta to end up getting sine squared of theta divided by cosine squared of theta plus cosine squared of theta divided by cosine squared of theta is equal to 1 divided by cosine squared of theta. Then what we see is that our middle term is going to simplify to 1. Then we have sine of theta divided by cosine of theta squared. So that's going to end up being tangent squared of theta. And 1 over cosine of theta, which is secant squared of theta. So just by dividing each one of our terms from our last identity by cosine of theta, we end up with an entirely new identity, which is tangent squared of theta plus 1 is equal to secant squared of theta, and any rearranging of this identity as well. If we do the same thing as before, so if we do the same thing with equation 5, but instead use sine of theta, we end up with cotangent squared of theta plus 1 is equal to cosecant squared of theta. So all of these identities are referred to as the fundamental identities. Identities 5 through 7 are also known as the Pythagorean identities, but we don't refer to them as that as often. So our fundamental identities that we're concerned with are going to be our quotient identities, our reciprocal identities, and these are technically our Pythagorean identities. But altogether, these are fundamental identities. These are going to be the important identities that we need to remember moving forward so that we can rearrange problems, solve problems a lot easier and a lot better, and things like that. So that's why we want to use these identities. So for our next problem, for example 2, we want to find the exact value of the expression without a calculator. So we have sine squared of pi over 12 plus 1 divided by secant squared of pi over 12. So we need to simplify this as much as possible. So since we already have sine squared pi over 12, we're just going to leave that. But we know that secant squared of pi over 12 is the same thing as saying 1 divided by cosine squared of pi over 12. So this really looks like 1 divided by cosecant squared of pi over 12. So if we have 1 divided by cosine squared of pi over 12, that is actually just going to simplify to sine squared pi over 12 plus cosine squared of pi over 12. And what we see here is that this looks very similar to one of our identities. This looks very similar to identity of sine squared theta plus cosine squared of theta is equal to 1. And actually, if we notice, we can just state that pi over 12 is theta. So it doesn't matter what theta is, as long as they're the same. So we don't have to actually write out theta. We can write an actual angle measurement like pi over 12. And either way, the answer is always going to be 1. So without a calculator, we've determined that this equation is just equal to 1. And this is just solely by using our identities. So they can be really helpful in solving problems, especially something like this, with some rearranging, they could be very simple.